Hey there, welcome back to the channel. So, in the previous video, we covered these three subchapters, and today we'll be covering at least three chapters, maybe just two, because I have only 45 minutes with me. So, this might be a 45-minute video, 46 plus minus 10, you know. So, let's get started. Converting an enumeration to and from a string. Okay, yeah, okay. So color this boom. Because operator doesn't know how to print a color, the compiler will implicitly convert color to an integer value and print that instead. Most of the time, printing an enumeration is an integer value such as 2 isn't what we want. Instead, we typically want to print the name of the whatever the enumerator represents, example blue. C++ doesn't come with an out-of-the-box way to do this, so we will have to find a solution ourselves. Fortunately, that's not very difficult. Getting the name of the enumerator. Is it something related to like changing some stuff related to the C out or something. Okay, so getting the name of the enumerator. The typical way to get the name of an enumerator is to write a function that allows us to pass in an enumerator and returns the enumerator's name as a string. But that requires some way to determine which string would be returned for a given enumerator. There are two common ways to do this. Wait, recording, audible. Okay, cool. Uh, in lesson 8.5, switch statement basics, we noted that a switch statement can switch on either an integral value or an enumerated value. In the following example, we can use a switch statement to set an enumerator and return the appropriate color string literal for that enumerator. Okay, so it's black, we return the string black, red, blue, and question mark. On stakes PR, color shirt blue, your shirt, get color name shirt, then it will return blue. Cool. Just give me a minute. So in the above example, on color we hold the numerator we passed in. Inside the switch we have the case label for each numerator of color. Each case returns the name of the appropriate color as a C style string. This C style string literal gets implicitly converted to an std string view, which is returned to the caller. Okay, the C style string literal gets implicitly converted to std string view. Okay, which is returned to the caller. We also have a default case which returns this in case the user passes in something we didn't expect. Okay, a reminder because C style string returns exists for the entire program. Yeah, that's what I was thinking about because like we are returning string views and after this function ends, these might be destroyed, but then I remember like these are C style string arrays and they are stored for the entire program, so they have an identifier. It's just that we can't use it. It's okay to return a string view that is viewing a C style string literal. When the string is copied back to the caller, the C style string literal being viewed will still exist. Yes. The function is constant XPR so that we use the color's name in a constant expression. Okay. It's a constant XPR function. Yeah. Uh, it should help us during initialization. The function is constant so that we use the color's name in a constant expression. Yeah. So while this lets us get the name of the enumerator, if we want to print that name to the console, having to do std_cout, get color name shirt isn't quite as nice as std_cout shirt. We'll teach std_cout how to print an enumeration in upcoming lesson. Yeah, that's what I was thinking about. And the second way to solve the program of mapping enumerators to strings is to use an array. Stud array, I guess. Stud array and enumerations. Okay, I'm not sure about that, but okay. Let's take a look at the input case. In the following example, we define a pet enumeration. Because pet is a program-defined type, the language doesn't know how to print a pet using std_cin. Okay. Uh, doesn't know how to input pet. I guess that's fair. One simple way to work around this is to treat an integer and use static cast to convert the integer to an enumerator, the appropriate enumerator type. So cat dog pig whale. There's a switch statement, get plate name, enter a plate name. We tell the user what each integer is mapped to. Get the input. You entered an invalid pet. Else static cast into pet. Split out, get plate name, cool. While this works, it's a bit awkward. Also know that we should only static cast pet input once we know input is in the range of the enumerator. Yeah, that's why the check is over here. Instead of inputting a number, it would be nicer if the user could type in a string representing an enumerator is up to pig, and we could convert that string into the appropriate pet enumerator. However, doing this requires us to solve a couple of challenges. First, we can't switch on a string, so we need to use something else to match the. Well, we can't switch on a string. Oh, you can't do that. Oh, right. Only char and int are allowed. Yeah, cool, fair. So we need to use something else to match the string the user passed in. The simplest approach here is to use a series of if statements. Yep. Second, what pet enumerator should be returned if the user passes in an invalid string? The question mark maybe. One option would be to add an enumerator to represent none invalid and return that. However, a better option is to use stood optional here. Okay, wait, let me guess what we will be doing. Okay, so this is const exp. So this is fair. Const ex. Oh, this is the answer. Okay, yeah, cool. Okay. So it gets a string view. If sp is equal to cat, return cat. This. Return optional. Boom. It we get it empty. So if not, yeah, then let pet and this. Cool. Cool. Sorry. In the above situation, we use a series of if else statement to do string comparisons to the user inputs. So if the user input string matches, if the user string matches an enumerator string, we return the appropriate enumerator. If none of the strings match, we return this. Yeah, cool. Which means no value. For advanced readers, know that the above solution only matches lowercase letters. If you want to match any letter case, we can use the following function to convert the user's input to lowercase. Yeah, C type, CC type, I guess. CC type. This function returns a std string that is in the lowercase version of the std string view passed in. Only 1:1 character mapping can be performed by this function to ASCII lowercase, std string view, std string lower, std string std transform, SV begin, SV end, std back insert a lower. I'm not sure what this is doing. Okay, so this function steps through each character in the std string view, converts it to a lowercase character using std to lower with the help of a lambda, and then appends that lowercase character to lower. Okay. Um, hmm. Similar to the output case, it would be better if we could use std_c in pet. We'll cover this in the upcoming lesson 13.5. So this is okay. Cool. Can we modify a std string view? Oh no, okay, no, you cannot modify the string view. Yeah, okay, fair then. That's fair. So introduction to overloading the I/O operators. In the prior lesson, 13.4, I'm converting an enumeration to and from a string. We showed this example. First, let me check like how big is this chapter. Yes, it's pretty small. So okay, let's get started. We show this example where we use a function to convert an enumeration into an equivalent string. Yup, yup. Although the above example works just fine, there are two downsides. You have to remember the name of the function we created to get the enumerator name in the function that we created. Yeah, having to call such a function adds clutter to our output statement. Ideally, it would be nice if we could somehow teach operator to output an enumeration so we could do something like this. Yup, introduction to operator overloading. In lesson 11.1, introduction to function overloading, we introduce function overloading, which allows us to create multiple functions with the same name as so long as each function has a unique function prototype. Using function overloading, we can create variations of a function that work with different data types without having to think up a unique name for each variant. Similarly, C++ also supports operator overloading, which lets us define overloads of existing operators so that we can make those operators work with our program-defined data types. Okay, C++ also supports operator overloading, which lets us define overloads of existing operators so that we can make those operators work with our program-defined data types. Okay, basic operator overloading is fairly straightforward. Define a function using the name of the operator as function's name. Add a parameter of the appropriate type for each operand. Okay, so define a function using the name of the operator as the function's name. Add a parameter of the appropriate type for each operand in left to right order. Okay, add a parameter of the appropriate type for each operand. Okay, one of those parameters must be a user-defined type, a class type, or a limiter type. Otherwise, the compiler will error. Hmm. So the return type of whatever type makes sense. Use a return statement to return the result of the operator operation. Okay, I'm not sure about this. Like I understood any of the stuff. While the compiler encounters the use of an operator in an expression, and one or more of the operands is a user-defined type, the compiler will check to see if there is an overloaded operator function that it can use to resolve that call. For example, given the expression x plus y, the compiler will use the function overload resolution to see if if there is an operator plus x and y function call that it can use to evaluate the operation. If a non-ambiguous operator plus function can be found, it will be called and result of the operation returned as a return value. And the result of the operation returned as a return value. Okay. Okay. I did not understand any of this stuff. We cover the operator overloading in much more detail in chapter 21. For advanced readers, operators can also be overloaded as member functions of the leftmost operand. We discussed this in 21.5. Overloading operator to print an enumerator. Before we proceed, let's quickly recap how operator works when we use for output. Consider a simple expression like std_cout this. Well, std_cout has a type std_oString, which is a user-defined type in the standard library and fires a literal type of int. When this expression is evaluated, the compiler will look for an overloaded operator function that can handle arguments of type std_oString and int. Hmm. It will find such a function and it will find such a function also defined as part of the standard IO library and call it. Inside that function, std_cout is used to output x to the console. Exactly how is implementation defined. Finally, the operator function returns its left operand, which is in this case std_cout, so that the subsequent calls to operator can be chained. Function returns its operand, which is in this which in this case it should see out so that the subsequent calls to operator can be chained. Okay. uh The compiler will look for overloaded operator function that can handle arguments of type std stream and int. It will find such a function, also defined as part of the standard IO library, and call it. Inside that function, std_cout is used to output x to the console, exactly how its implementation defined. Finally, the operator this function returns its left operand, which is in this case std_cout, so that in subsequent calls to operator can be chained. With the above in mind, let's implement our overload. Okay, I did not understand any of that. 15 minutes video. I think I can set a timer for 30 minutes more. Okay. Yeah. What it is, operator overloading lets you teach C++ how operators like plus, minus, this should work with your own type classes or enums. Why it's useful, you can use familiar symbols instead of long function names, making code easier to read. How it works, an operator is just a function with a special name like operator plus. The function takes inputs operands left to right, must use at least one user-defined type, returns a result. What the compiler does when it sees something like x plus y and x or y is your type, it looks for a matching operator plus function and calls it. Example idea this works because there's an overloaded function operator that knows how to print an int. You can write your own operator this, so should see out color red print something meaningful. Key takeaway: operator overloading is equal to make operators work naturally with your own types. Okay, fine. Let's check how it works. So stdio streams, it returns a stdio stream. Operator this. Okay. Teach operator how to print a color. Stdio stream is the type of std_cout, std_cerr, etc. The return type and parameter type are references to prevent copies from being made. The return type and parameter type are references. Hmm, hmm. And also out. Print our colors name to whatever output string. Yeah, I'll out stdio stream this. So when we call this, when we are not calling it. So stdio stream is this. This is the operator. This is the stream out and color. But I'm not understanding the syntax, like what is happening over here. Are we supposed to mention operator over here? Can I do the same thing with class, I guess? So color shirt blue, face shirt, it works. Your shirt is blue. Okay, I'll look at that afterwards. So let's unpack our overloaded function a bit. What's the name of the name of the function? Like, how much is this remaining? Yeah, okay, not much. First name of the function is operator this operator less than this done. Since that is the name of the operator we are overloading, operator has two parameters. The left parameter, which will be matched with the left operand, is our output stream, which has type std_o stream, std_o stream, std_output stream. Yep. We use pass by non-const references here because we don't want to make a copy of the std_output stream object when the function is called, but the output stream object needs to be modified in order to do output. The right parameter, which will be matched with the right operand, is our color object. Since this conventionally returns its left operand, the return type matches the type of the left operand, which is with not understanding any of this. Since operator conventionally returns its left operand, The return type matches the type of the left operand, which is stored OS stream reference of output stream. Let's look at the implementation. Output string object already knows how to print a string view using operator this. This comes as a part of the standard library. So out get color simply fetches our color's name with a string view and then prints it to the output stream. Note that our implementation uses parameter out instead of std_cout because we want to allow the caller to determine which output stream. Okay, instead of std_cout because we want to allow the caller to determine which output stream they will output. Example std_cer color should output to std_cer not std_cout. Yeah, fair. Returning the left operand is also easy. The left operand is parameter out, so just return out. Putting all together, when we call std_cout shirt, the compiler will see that we have overloaded operator this to work with objects of type color. Our overloaded operator function is then called with std_cout as the out parameter and our shirt variable, which has value blue as parameter color. Since out is a reference to std_cout and color is a copy of enumerator blue, the expression out this prints blue to the console. Finally, out is returned back to the caller in case we want to chain additional output. Okay, so overloading operator this to input an enumerator. So this is the input one. Okay, similar to how we were able to teach this. So okay, let me write this one. So I assume okay, I can't guess. So yeah, still input stream and this. Yeah, okay, okay. So this is fine. Get met from string and get the string view one and get met from string. Okay, so fine. So get input string. So this is the input string. We get this is stored optional pet match. Get pet from string. This so we get a pet. If match, if we found a match, if it was true instead of optional, it is equal to dereference match, still optional to get a matching enumerator, and then return input. Fair. We didn't find a match, so input must have been invalid. So we will set input stream to fail state. So input dot set state stood iOS base fail bit on extraction failure operator zero initializes fundamental types. Uncomment the following lines to make sure this operator do the same thing that. Hmm. Uncomment the following line to make this operator do the same thing. Zero initializes fundamental type. Okay, so let's try this. Okay. Um, yep, that was not valid. And if I go ahead and uncomment this, oops, sorry. Oh, no, sorry. Yeah, okay, let's try this. So it should zero initialize, so I should get an output as 0. It works. Okay, so what did they mean? Is it cat every single time? So let's say I do dog. Let's say dog. So okay, if I found a match, you choose this, else should cin.clear reset the input stream to good. Scene.ignore numeric limits this. Your pet was not valid. Okay, there are a few differences from the output keys worth noting. First, std scene has type input stream, so we use a std input stream reference as the type of a left parameter and return the value instead of output stream. Second, the pet parameter is a non-const reference. Sorry, this allows our operator to modify the value of the right operand that is passed in if our extraction results in a match. This allows our operator to modify the value of the right operand that is passed in if our extraction results in a match. Hmm. This allows our operator to modify the value of the right operand. Modify the value of the, this allows us our operator to modify the value of the right operand that is passed in if our extraction results in a match. So key insight, our right operand pet is an out parameter. We cover our out parameters in lesson 12.13 in and out parameters. So yeah, sure. Our pet over here. This is what they are talking about. If pet was a value parameter rather than a reference parameter, then our operator function would end up assigning a new value to a copy of the right operand rather than actual right operand. If pet was a value parameter rather than a reference parameter, then our operator function would end up assigning a new value to our copy of the right operand rather than actual right operand. We want our right operand to be modified in this case inside the function. Okay, so they're saying that if a if pet was a value parameter rather than a reference parameter, then an operator function would end up assigning a new value to the copy of the right operand rather than an actual right operand. We want our right operand to be modified in this case. Yeah, that's why it's a reference. So inside the function, we use operator this to input a std string, something it already knows how to do. If the value of the user enters matches one of our pets, then we can assign pet the appropriate enumerator and return the left operand in. Sorry. So if the value of the user enters if the value the user enters matches one of our pets, then we assign pet the appropriate enumerator and return the left operand in. If the user did not enter a valid pet, then we handle the case by putting std into failure mode. This is the state that std typically goes into when an extraction fails. The caller then check std to see if the extraction succeeded or failed. Related content in lesson 17.6. This we show how we can use std to make our input and output operators less redundant and avoid having to modify them when a new enumerator is added. Okay, cool. So I guess we have 17 minutes left. Um, well, not 17, I guess. So this is near the okay. So this is so I have 16 minutes. So this will be a 46-minute video. So in 16 minutes, can I cover this? Yeah, I can do it maybe. Although unscoped enumeration. So scoped enumerations. Okay, cool. We have covered unscoped enumeration, so this will be something new. Although unscoped enumerations are distinct types in C++, they are not type safe and in some cases will allow you to do things that do not make sense because of the following case. Yeah, okay. So enum color, enum fruit, banana apple, red banana. If color is equal to fruit, If color is equal to fruit, so comparator, the compiler will compare color and fruit as integers. Oh, okay. So red is 0, banana is 0, so they are same, color and fruit are equal. Yup. When color and fruit are compared, the compiler will look to see if it knows how to compare a color and a fruit. It doesn't. Next, it will try converting color and or fruit to integers to see if it can find a match. Eventually, the compiler will determine that if it converts both to integers, it can do the comparison. Since color and fruit are both set of enumerators that convert to integer value 0, color will equal fruit. This doesn't make sense semantically since color and fruit of are from different enumerations and are not intended to be comparable with standard enumerators. There's no easy way to prevent this. Because of the challenges as well as the namespace pollution problem, unscoped enumeration defined in the global scope put their enumerators in the global namespace. The C++ designer determined that a cleaner solution for enumeration would be of use. So, scoped enumerations, okay. That solution is a scoped enumeration, often called as enum class in C++ for reasons that will become obvious shortly. So scoped enumerations work similarly to unscoped enumerations, but have two primary differences. They won't implicitly convert to integers, and their enumerators are only placed into the scope region of the enumeration, not into the scope region where the enumeration is defined. Scope region of the enumeration, not the scope region where the enumeration is defined. Okay, so inside a class. To make a scoped enumeration, we use the keywords enum class. The rest of the scoped enumeration definition is the same as the unscoped enumeration definition. Here's an example. Okay, so enum class color. Enum class defines this as a scoped enumeration rather than an unscoped enumeration. Red, blue. Okay, enum class fruit. Banana, apple. Hmm. So color red. Fruit, fruit, banana. Red is not directly accessible. We have to use color red. And banana is not accessible. We have to use this. So if color equal to fruit compiler, the compiler doesn't know how to compare different types, color and fruit. And why is that? This program places a compiler on line 19 since the scoped enumeration won't convert to any type that can be compared with another type. Since the scoped enumeration won't convert to any type that can be compared with another type. As an aside, the class keyword along with the static keyword is one of the most overloaded keywords in the C++ language and can have different meanings depending on the context. Although scoped enumerations use the class keyword, they aren't considered to be a class type, which is reserved for structs, classes, and unions. So enum struct also worked in this context and behaves identically to enum class. However, use of enum struct is non-idiomatic, so avoid its use. Okay, first of all, let me ask a question over here. Why wasn't it able to implicitly convert to int? Why can't it recognize the types? Sorry, it's 12 minutes to go. Enum class is strongly typed. That means its values do not automatically turn into int. Why no implicit int conversion? To prevent bugs, old enums could silently convert to int, causing incidental comparisons. Enum class disables this on purpose. Why it can't compare color and fruit? They are different types. Even if both store numbers underneath, C++ treats them as unrelated. Red and banana are not just numbers, they belong to a different enums. A key idea enum only compares with the same enum type unless you explicitly convert them. Hmm. How is it strongly typed? Static cast and Stop the implicit conversion. Means the enum has its own distinct type, not just a number. With enum class, C++ removes automatic conversions to int. The compiler enforces this by not defining any implicit conversion operator to int. Only allows explicit cast, static cast, so this is illegal. Okay, sure. Scoped enumerations define their own scope regions. Unlike unscoped enumeration, which place their enumerators in the same scope as the enumeration itself, scoped enumerations place their enumerators only in the scope region of the enumeration. Scoped enumerations place their enumerators only in the scope region of the enumeration. In other words, scoped enumerations act like a namespace for the enumerators. This built-in namespacing helps reduce global namespace pollution and the potential for name conflicts when scoped enumerations are used in the global scope. To access a scoped enumerator, we do so just as if it was in a namespace having the same name as the scoped enumeration. To access a scoped enumerator, we do so as if it was in a namespace having the same name as the scoped enumeration. Okay, so enum class this definition defines this as a scoped enum rather than an unscoped enum. Red is considered part of the color scope region. Red not allowed. Color red still not allowed. Why? Stood cout doesn't know how to print. Oh, okay, okay. Doesn't know how to print this. Will not implicitly convert to int. Color, uh, color blue. Okay, so that's fair. Because scoped enumerations offer their own implicit namespacing for enumerators, there's no need to put scoped enumerations inside another scope region, such as namespace, unless there's some other compelling reason to do so, as it would be redundant. Scoped enumerations don't implicitly convert to int. Unlike non-scoped enumerations, scoped enumerators won't implicitly convert to int. In most cases, this is a good thing because it rarely makes sense to do so, and it helps prevent semantic errors such as comparing enumerators from different enumerations or expressions such as red plus 5. Fair. Note that you can still compare enumerators from within. Oh, by the way, let's test this. So ci this stood cout. What was it? It was pet, right? It's a pet. Pet fail plus 5. Let's see what it does. It's 8. Okay. Still compare intervals from within the same scope derivation since they are of the same type. Okay. So color shirt, color red is if it is equal, comparison is okay, and this is fine too. There are occasionally cases where it is useful to be able to treat a scoped enumerator as an integral value. In these cases, you can convert a scoped enumerator to an integer by using static cast. A better choice in C++23 is to use std2 underline defined in the utility header, which converts the enumerator to a value of the underlying type of the enumeration. So, okay, enum class color blue, color won't work because there's no implicit conversion to int. Static cast, explicitly conversion to int will print 1. Std2 underline convert to underlying type will print 1. Okay. Conversely, you can also static cast an integer to a scope enumerator, which can be useful when doing input from users. Okay, enter a pet input static cast this. Yeah, so it works for scoped enumerators too. As of C++17, we can list initialize a scoped enumeration using an integral value without the static cast, and unlike an unscoped enumeration, we don't need to specify a base. For an example, this. Okay, this is okay. Hmm. You can list initialize the scoped enumeration using an integral value without the static cast, and unlike an unscoped enumeration, you don't need to specify a base. This is only allowed at initialization. It is a one-way conversion into enum, not enum to int. Or allow it safe at creation type, no ambiguity after the object exists. Why still no implicit enum to int conversion? That's where the bug happens. This is where strongly typed because why doesn't it why doesn't it work for what was it called? Uh, Unscoped enumeration. Also give what the code look like and how it feels. On weekly type, we already convert to int. CSS does not allow list initialization from an int. Yeah, okay, this is not allowed. Fair. Allowed in C++17 works. Sure. Okay. Favor scoped innovation over unscoped innovation unless there's a compelling reason to do so. Otherwise, despite the benefits that scoped innovation offer, unscoped innovators are still commonly used in C++ because there are situations where we desire the implicit conversion to int. Doing lots of okay, unscoped innovation is still commonly used in C++ because there are situations where we desire doing lots of static cast gets annoying and we don't need the extra name spacing. Sorry. Easing the conversion of scoped enumerators to integers, advanced. Okay, scoped enumerations are great, but the lack of implicit conversion to int can sometimes be a pain point. If you need to convert a scoped enumeration to integer often, example cases where we want to use scoped enumerators as an indices, having to use static cast every time we want to convert can clutter our code significantly. If you find yourself in the situation where it would be useful to make conversion of scoped enumeration, then we can just make a function, right? Make conversion of scoped enumeration to integer easily. A useful hack is to overload the unity operator plus to perform this conversion. Okay, for underlying type thing. Overload the unity operator to convert an enum to an underlying type. Adapted from Stack Overflow. This thanks to Pixel Commist for the idea. In C++23 you can do okay, fair. This const exp auto operator plus, so this is plus whatever the type we get. This is the unity one. No except I don't know what that is. It returns a static cast underwriting. Yeah, that's what I was saying. Like make a function, when this is an overloaded one, it's a template function or something like that. So whenever we say plus animals and elephant, what it does is that it gets animals elephant, a single template, no except auto operator this static cast, and it will return underlying type T and A of A. Okay. Underlying type of the this animals elephant. Okay, converts animal elephant to an integer using unity operator. Cool. This prints 3. This method prevents unintended implicit conversion to an integral type, but provides a convenient way to explicitly request such conversions as needed. So we have 2 minutes remaining. Using enum statements in C++20. Introduced in C++20, using enum statement imports all of the enumerators from enum into a current SOAP. When used with the enum class type, this allows us to access the enum class enumerators without having to prefix each with the name of the enum class. This can be useful in cases where we would otherwise have many identical repeated prefixes, such as within a switch statement. So imports all the enumerators from the enum into this current scope when used within an enum class type. This allows us to access the enum class enumerators without having to prefix each with the name of the enum class. Yeah, okay. So if you do this, enum class color, we have to access with color black, color red, color blue, and using enum color, bring all the color enumerators into the current scope. So use 20, we can use the yeah, okay, cool. So search this, return black, return blue, return this, color shot this, get color shot, cool. In the example, color is an enum class, so we normally would access the enumerators using a fully qualified example color blue. However, within the function getColor, we have added the statement using enum color, which allows us to access those enumerators without the color prefix. This saves us having multiple redundant obvious prefixes inside the switch statement. Quiz time. Define a enum class called animal that contains the following animals: pig, chicken, goat, cat, dog, duck. Write a function named getAnimalName. Okay. Define a enum class named animal. So okay, let's do it. So hash include IO stream first of all. So let's say this was enum class. What is supposed to be name? Animal. Let me. So our time is up actually, but I'm just going to take another 5 minutes, I guess. Okay. So define a enum class animal that contains the following animals: pig, chicken, goat, cat. Pig, chicken, goat, cat, duck, dog. Okay. Just going to copy this, paste this. Okay, I actually needed that. So write a function named getAnimalName that takes an animal parameter, uses a statement to return the name for the animal as a string view. Okay. Write a function named getAnimalName that takes an animal parameter and uses this. Okay. So getAnimalName returns a string view. The function name is getAnimalName. It takes an that takes an animal parameter and uses a string. Okay, okay. It takes an animal and uses a string statement to return the name of for the animal as a string view or string if you are using C++ 14. Write another function named okay. So let's complete this first. So using enum class, what was it called? Using enum animal, I guess, right? Using enum, yeah, cool. I'll set up a switch statement. Well, the switch statement will be based upon color, I guess. Yeah, the color we get. So this is the temp. So for the first case, which is yeah, okay, I can't add case right now. The case will be, let's say, pig, chicken, goat. Yeah, pig. Uh, return pig break. Should I add break every single time? No, okay. Yeah, that's returning. So case semicolon, right? Yeah, yeah. Cool, cool. Case chicken return chicken. What is happening? Wait, am I missing something? Color this semicolon and colon. Case goat return goat. I guess it might be because there is no break statement, but okay, that's fine. So cat return cat case dog return dog And then there's case dark that it returns dark, and there is a default case in which we should return still optional, right? Yeah, still optional string view, sorry. How about that? And the next function, write down the function name print number of legs that uses a split statement to print the number of legs each animal walks on. Make sure both functions have a default case that prints an error. Okay, I need to get going actually. Make sure both functions have a default case that prints an error. A default case that prints an error. It's 7:39, 7:40. Okay, I need to get going. Thanks for watching this video. I'm Adit Vashani, and I am an engineer for fun. Bye.